Hello APC Mechanics students in Unit 3 Work Energy and Power, Class 7, Conservation of Energy, Part 1. Then Section 1, Mechanical Energy and its Conservation. An isolated system is a set of objects that interact only with each other but not with the rest of the universe. For an isolated system, the total energy is conserved. Energy is neither created nor destroyed, and this is known as the law of conservation of energy. The evolution of a system is dictated by forces, as we have seen explicitly in Unit 1 and Unit 2. However, an alternative promising approach would be the evolution of the system via energetic approach. We define the mechanical energy E of a closed system to be the sum of kinetic and potential energies. So here what I'm saying is that E would represent the mechanical energy. So E is the mechanical energy, K is the kinetic energy, and UG is the gravitational potential energy, and US is the elastic potential energy. The mechanical energy E of a closed system is conserved if there are no conservative dissipated forces acting on the system, like friction and drag force. So basically, in the absence of frictional forces, mechanical energy is always conserved. Impact speed of a free fall. We have derived the expression of the impact speed of a free fall in Unit 1 via kinematics approach, and the result is given by V is radical to GH with no initial velocity, and we have generalized that for a given initial velocity independent of the direction is given by radical to GH plus V0 square. These expressions can be determined again via energetic approach. Consider an object of mass m released from rest at a height h. Now we have no initial speed. It will reach the ground after a certain time lapse. We are interested in determining the velocity v before the impact. We know the result. If there is no initial speed, it's given by radical to gh. For a free fall motion, a resistance is negligible, then the mechanical energy of the system object Earth is conserved. So here we're assuming there is no resistance. Whenever there is no resistance, then the mechanical energy is conserved because there are no non-conservative forces. Then the mechanical energy of the system object Earth is conserved. Why we're talking about the system object Earth? Because whenever we include the object Earth, this means that we have included the pull of gravity. Now we will consider 2 points A and B. A will be the initial point where we have left the ball, and B would be just the ball before the point before the ball momentarily hits the ground. And we can say that the mechanical energy at the point B is equal to the mechanical energy at the point A. This means that the kinetic energy at B plus the gravitational energy at B is equal to the kinetic at A plus the gravitational at A. Now why we didn't include the potential energy elastic of a spring? Because here we don't have springs. Choose the PE level to be the ground. So remember that whenever we're dealing with the gravitational potential energy, we need to set our PE level, and it's usually chosen to be the lowest point in our system, and in this case it's set to be the ground. And in this case we can directly say that the potential energy gravitation at B is 0 because the ball at the point B will almost be at the ground. Moreover, we can say that the kinetic energy at the point A is 0 because we have no initial speed. Now as you can notice that from this equation we can read that the kinetic energy will be the potential energy gravitational will be transformed into kinetic energy without any loss because we don't have frictional forces, which means half mv squared is equal to mgh. M with m cancel, which means that v is given by radical to gh. Then the impact speed of a free fall with no initial velocity is given by radical to gh, which is exactly the same result that we have determined in Unit 1. Now we will discuss the conservation of energy. Initially, the system object Earth possesses certain amount of gravitational potential energy UG equal to the mechanical energy E of the system. So here what I'm saying is that at the point A, the energy of the system is completely gravitational because the speed is 0. And this can be pictorially represented in an energy diagram. So here you notice that the energy bars, so for each of the following graphs we have two energy bars, one for the gravitational potential energy, one for the kinetic. Initially this represents the point A, and this represents the point B, yet I didn't place the energy diagrams here. At the point A, all of the bar levels are up for the gravitational potential energy. During the downward motion of the object, there will be a complete conversion from gravitational potential energy to kinetic, As the object starts falling, the object will lose UG and gain kinetic energy. So as the ball moves from A to B vertically downward, H will decrease, which means MGH will decrease, which means that the system will lose its potential energy gravitational, but we know that energy is neither created nor destroyed. This loss of gravitational potential energy would be gained as kinetic energy. For this reason, here you can notice that initially we started with 4 bars. Now for UG we have 3 bars, and here we have 1, but in total they are still 4 because there is a complete conversion of energy. At a point in space, UG and K, they equalize. So we expect that at the point in space they will be equal, yet we don't know if this point that we're talking about is exactly in the middle, or in the first half, or in the second half. We're just saying that they will equalize at some point. After that, the kinetic energy remains to increase. At the PE level, UG drops to 0 and E is completely converted to kinetic energy. And as you can notice that for all 5 diagrams, we have 4 energy bars, which means that the energy is always conserved. Since there is no resistance, frictional forces, then the mechanical energy of the system is always conserved. Now let's derive the expression of the impact speed given an initial velocity. The same object is dropped again from the same height given an initial velocity v0. We're interested in determining the velocity before the impact. For free fall motion, a resistance is negligible, so whenever there is no frictional forces, the mechanical energy is conserved. And in order to determine the impact speed, we need to choose 2 points. We will go for A and B. A is the initial point and B is the final point, and we will say that the mechanical energy is conserved. EB is equal to EA. At the point B we have both kinetic and potential. At the point A we have kinetic and the potential. And now whenever I refer to the potential energy, I mean gravitational, because here we don't have springs. Now we need to choose our PE level. That would be the lowest point in our system, which is the ground. Then the gravitational potential energy at B is 0. Here we cannot say that kinetic energy at A is 0 because we have initial speed. And now we can say half mv square B is equal to half mv square plus mgh. All of the 3 masses cancels and we're left with this, which means that vb square is equal to v square A plus 2gh, and indeed vb is the radical to gh plus va square. Then the impact speed of a free fall with no initial velocity is given by radical to gh plus v0 square, where v0 is the initial speed, which is the same exact result that we have determined or we have put forward in unit 1. What is beautiful about this approach is that no orientation is required, and we don't care about how initially the object has been launched upward, downward, or even at an angle. So basically in kinematics, or in both units 1 and 2, what was difficult to carry is the forces, the directions, the projections. What is so nice about energy, and we can say it is so beautiful, that we don't care about directions. We don't care about orientations. We just choose an initial point, a final point, and we can carry on the calculation. Initially, the system object Earth possesses certain amount of gravitational energy and gravitational potential energy and kinetic energy, and this can be pictorially represented here. That would be the point A, and that would be the point B. At the point A, we have certain amount of both gravitational potential energy and kinetic energy. It might be the kinetic energy to be greater than UG, but in this case the comparison is not important. We're interested in how the energy will be converted through different states. During the downward motion, the object will lose gravitational potential energy, and this loss will be completely converted to kinetic energy. As the object starts falling, as we said, UG will be lost and K will be gained. At the point in space, UG and K will equalize. Okay. At the PE level, UG drops to 0 and is completely converted to kinetic energy. And as you can notice, for all 4 diagrams, the sum of the energy bars is 4. Here we have 3, here we have 1. Why at the final position we have here 4 and here we have 0? Because we're at the PE level. Since there is no resistance, frictional forces, then the mechanical energy of the system is always conserved. Now, section 3, motion along a frictionless ramp. We have derived the expression of the impact speed of an object sliding on a frictionless ramp in units 1 and 2 via kinematics and dynamics. The result is given by also v is radical to gh with no initial velocity, radical to gh plus v0 square with initial velocity. These expressions can be determined via energetic approach again. We remember that here h represents the vertical height and not the distance traveled along the ramp. The distance traveled along the ramp would be given by d sine theta. If you want to express it in terms of that, d would be the actual distance traveled along the ramp and theta would be the angle of inclination. Consider an object of mass m released from a height h on a frictionless ramp inclined by theta. Why we have mentioned that the ramp is frictionless? This is important for us because we know that whenever there is no friction, then the energy of the system will be conserved. So let's consider the initial point, which is the point at the top of the ramp. We have no initial velocity, and the other point, which is the bottom of the ramp, and h would be the vertical distance from the up to top, from up to bottom. We're interested in determining the velocity at the bottom of the ramp. All frictional forces are neglected, then the mechanical energy of the system is conserved. We will consider 2 points A and BA at the top, B at the bottom, and we will say that energy at B is equal to energy at A. What types of energy do we have? We have combination of kinetic and gravitational potential energy. The energy of the spring here can be ignored because we have no springs. Now choose the PE level to be the bottom of the ramp. At the point B, the UG would be 0 because we are at the PE, and initially the kinetic energy at A would be 0 because we have no speed, which means that half mv square is equal to mgh. M with M would cancel, and we're left that V is radical to gh based on the fact that h is the vertical height going from A to B. Then the impact speed of an object sliding on a frictionless ramp with no initial velocity is given by radical to gh, which is the same result. The vertical height h can be expressed in terms of the covered distance d along the ramp and the angle of inclination theta, as h is d sine theta, and the speed can be expressed as radical to gd sine theta. The other expression would be given by, so this is for with no initial velocity. With initial velocity, it is given by radical to gh plus v0 square for the case of an object sliding along a frictionless ramp with a given initial velocity v0, and this can be left for you as an exercise. Initially, the system object Earth possesses certain amount of gravitational potential energy Ug equal to the mechanical energy A of the system. So here again we're referring to the energy bar diagrams. That would be A and that would be B. Initially, all of our energy is contained as a gravitational potential energy dictated by 4 bars. During the downward motion of the object, there will be a complete conversion from gravitational potential energy to kinetic. As the object starts sliding, the object will lose Ug and gain kinetic energy. At a point in space, Ug and K will equalize. Now, so basically, let me say this is the midway of the vertical distance. We don't know if they will equalize at the first part or the second part. The important thing is that they will equalize because there is a continuous conversion. At the PE level, Ug drops to 0 and E is completely converted to kinetic energy. Since there is no resistance, frictional forces, then the mechanical energy of the system is always conserved. And now for the rest of the video, we're gonna do some exercises. Exercise 1, students set up an experiment with a small block on a ramp. The block of mass m is 3 kg is released from rest at the top of the curved ramp. The length of the ramp as measured along the curve is L is 3 meters and the height h is 1.5 meters as shown. There is negligible friction between the small block and the ramp, which means frictional forces are neglected. That means that we can use the conservation of energy. And we need to determine the speed of the block at the bottom of the ramp, which is the point B here, and let me say this is A. And remember that at this point we have 3 laws that we can implement in order to solve for a problem, given by Newton's second law, given by work energy theorem, and given by the conservation of energy. And whenever we need to use this law, we need to mention that we're using these laws. However, you can think about using Newton's second law here, but it will be so difficult because the shape that we're moving along is a curvature and it will be difficult to handle vectors along this curve. Work energy theorem requires the work done by forces. We can use the work energy theorem, and we can use the conservation of energy. Let me do it both ways, work energy theorem and the conservation of energy. Let me start first by the conservation of energy. We need to mention that apply conservation of energy. Why we're doing so? Because there is no friction. Usually this statement they give it half a mark. Then we will say that the energy at B equals to the energy at A. We're talking about kinetic energy at B plus gravitational potential energy at B is equal to kinetic energy at A plus gravitational potential energy at A. I will choose this to be my PE level. Then directly that would be 0, and that would be 0 as well because our initial speed is 0. It's trapped from rest. Then what do we have here? Half mv square at the point B, which we're interested in determining, is mgh, and that would be v is radical to gh. Now what does h represent? H represents the vertical height, which is 1.5. That would be the radical of 2 multiplied by 10 multiplied by 1.5, and that would give us a value of 5.5 meter per second. I know that this is an MCQ and you can directly know the result by v is radical to gh. However, I'm trying just to explain different approaches. Now also we can do it using the work energy theorem. For the work energy theorem, we need to say apply the work energy theorem, which means that the variation in the kinetic energy is equal to the work done by the all external forces. So kinetic energy final, which is at the point B, minus the kinetic energy initial, is equal to the work done by the pull of gravity plus the work done by the normal push plus the work done. Okay, so this is it. These are the only two forces. The work done by the normal push is always 0, and the work done by the pull of gravity, if we're going up it's negative, if we're going down it's positive. If we're going down by vertical distance h, then that would be mgh. That would be 0 because no initial speed, and half mv square, which give us the same expression, which is v is radical to gh, and we're left with B as the correct answer. Exercise 2. Identical blocks 1 and 2 start from rest at a height h, travel down two differently shaped tracks on identical rough horizontal surfaces as shown in the figures above. Both tracks are frictionless and both makes a smooth transition onto a horizontal rough surface. Now here we don't have friction, no friction, and here we have a rough surface, which means we have friction. Block 1 comes to rest at a horizontal distance t1 from the bottom of the track. Which of the following best describes and explains the horizontal distance t2 that the block 2 travels before coming to rest? So block 2, whenever it reaches this point, it will become at rest after a horizontal distance t2. We're trying to compare d1 and d2, and this depends on what? Depends on the speed of the object at this point. However, since both ramps independent of the shapes, because blocks 1 and 2 are released from the same height, which means that they will acquire the same speed at the bottom of the ramp, independent whether blocks 1 and 2 are identical, because we know that the expression of the speed is given by radical to gh and it is mass independent. Now, because these two blocks will reach these points at the bottom of the ramp with the same speed. Indeed, they're telling us they are identical, so we can ignore the fact that we're differentiating between the masses. So they are identical, so whenever they reach this point they will acquire the same speed, which means exactly they will stop at the same distance, which means that d1 equals to d2 because they start at the same height. Finally, exercise 3 as an exit ticket for today's video. 3 identical spheres are thrown from the same height above the ground. Sphere X is thrown vertically up, sphere Y is thrown horizontally, and sphere Z is thrown vertically down, as shown in figures 1, 2, and 3 above, respectively. All 3 spheres are thrown with the same speed. Her resistance is negligible, so notice that they are thrown with different velocities but with the same speed because the direction is different. Which sphere or sphere initially collide with the ground with the greatest speed? We know that all of the 3 will have the same speed, because forces are negligible, resistive forces, which means all of them will acquire a speed given by radical 2gh plus v0 square, in which v0 is the magnitude of the velocity, which is the speed, and all they have the same height, independent of the direction of the velocity. And then that's it for me in this video guys. See you soon in a new one.